Hi, today we're going to go through the PAT paper from 2016, looking at question 16. So question 16, we're saying a negative point charge minus Q lies between two positive charges, Q1 and Q2. And we're told Q1 lies at the point x equals 0 and Q2 at x equals a. We're asked for the cases Q1 equals Q2 and Q1 doesn't equal Q2. Find where minus Q experiences no net force. So let's start with Q1 equals Q2. Well, we know that Q1 lies at x equals 0 and Q2 lies at x equals to a. So Q is going to be somewhere along this line, and we'll just place it here. And we'll say it's at some distance x from Q1. Well, this one's actually straightforward enough. Because Q1 is equal to Q2, they're both going to pull on Q with exactly the same force. So we're going to have a force in this direction equal to the force in this direction. So clearly for Q to experience no net force, we require that Q is exactly halfway between Q1 and Q2. So we see that it must lie at x equals to a over 2. What about when Q1 doesn't equal to Q2? So we're going to use the same diagram as above. Now we want no net force, so we want the force from Q1, F1, to be equal to the force from Q2, F2. So we require F net, which is the difference between the two forces, to be equal to 0, i.e. the forces from the two charges are equal. And what is the force from two charges? Well, we know that the electric force, F, is equal to K times Q1, Q2 over R squared, where Q1 and Q2 are just two charges. So in our case here, we have K times the first charge Q1 times little q over the distance between them, x squared, has to be equal to K times, well this time it's Q2 times little q over the distance between them. Well, that's a minus x all squared. Cancelling off our k's and our q's, we see that Q1 times a squared minus 2ax plus x squared is equal to Q2 x squared. Okay. In fact, writing that out was not the best way to go. So we'll actually rewrite this as Q1 into a minus x squared. And the reason we don't want to expand it out is we want to find an expression for x in terms of a. So if we square root both sides, we see in fact that Q1 into a minus x is equal to the square root of Q1 plus or minus the square root of Q2 times x. Well, therefore, Q1 square rooted a equals to Q1 square rooted x plus or minus Q2 square rooted x, which implies that x is in fact equal to Q1 square rooted over Q1 plus or minus Q2 all square rooted times a. Now we have to think, when can we have these plus or minus cases? Well, we're going to have disregard the case where we have a negative sign at the bottom. So we're just going to place that with plus, and we'll justify that now. So the reason we can't have the negative, the Q1 subtract Q2, is because firstly, if Q1 were to equal Q2, we'd have Q1 square rooted over 0 because they'd be equal. So that wouldn't work. So we have an infinity, distance of infinity. Let's imagine the case where Q2 was very slightly less than Q1. Well, what that would mean is the square root of Q1 minus the square root of Q2 would be a very, very small number. And therefore, Q1 divided by this very small number will be absolutely massive, but negative. So it would mean that our x value is right the way down in towards minus infinity. However, we said that Q1 and Q2 are only slightly different in magnitude. So that would mean that this would have to require Q2 to be exceptionally large to produce enough force to pull it back and have no net force. And in fact, you wouldn't have no net force over here, because if these are both positive charges, if it's at a negative coordinate, then we're going to have both charges pulling on the negative charge. So there can't be no net force. Similarly, if Q1 is greater than Q2, then we're going to have a very large positive value. So we're going to have that over here. And so again, we have a negative charge being pulled by two positive charges. So that simply won't work. So we have to see that it lies in the middle of them, which corresponds to the plus value.